Okay, now look at question 2a. In question 2a, we are trying to determine if v, that vector v has three components. Okay, it's a vector in R3. V has three components: 2, -3, and 4. Okay, we are trying to determine if that vector v is a linear combination of I, j, and k or not. I, j, and k are standard basis vectors in R3. Okay. Anybody want to tell me the answer? Is V a linear combination of I, j, and k?
Yes,
Yes, yes. In order to answer that question, we need to check: is it possible to write V as a linear combination? Are there three numbers? I mean, okay, are there three numbers having the condition that V is a number times I, and then plus another number times j, and then plus the third number, and then times k? Now let's recall V. V is the vector. V is the vector with three components: 2, -3, and 4. 2, -3, and 4. Okay. V has three components: 2, -3, and 4. Okay. Anybody want to tell me the three numbers, three question marks I'm looking for? How to write V as a linear combination of I, j, and k? I'm looking for the three numbers, three question marks. In this particular case, V is equal to, I think it's too simple. I think all of you guys know that. So maybe not all of you guys. V is a linear combination of, 2, -3, and 4. Yeah, that's correct. Okay. V is written as a linear combination of I, j, and k as 2 times I, then plus -3 times j. I can write as -3j, right? And then plus 4k. That's how can we write V as a linear combination of I, j, and k. So just refer to your memory about the definition of a linear combination. What do we mean by linear combination? Okay. That's a three-dimensional case. After that, I guess we are ready to talk about more general case. Okay. Earlier question, essentially we guess the numbers, right? Or it's easier to see the numbers. Now look at question A. So that's question 1A on the handout. That's question 1A on handout number 5, I think. Okay. If you don't have the files, all the files are on D12. Okay. In particular for the new guy who's just joined the class. All right. Now we're trying. In this case, to answer that question, it's possible to guess. I guess in the past years, so many people just guess. Okay. Some people just guess. Okay. Some smart guys, they just guess. But I will show you a formal way. Okay. To determine if the vector, so now let's say 3, -5. These are the vectors in R2. Okay. Now let's say if we're trying to determine if the vector with two components, 3, -5 is a linear combination of the other two vectors. We're trying to look for two numbers: a scalar, a number before 1, 3, the vector 1, 3, and another number before 2, -1. Mute your microphone, please, if you don't have questions. You have. Simran, so mute your microphone, please. Another number times, so now let's say 2, -1. Now, again, to determine if that vector is a linear combination of the two vectors 1, 3, and the 2, -1, we need to determine if there are two scalars or two real numbers satisfying that equation. So this time it's not too easy to guess, at least, right? It's not too easy to guess. You imagine if I give you some more complicated vectors, it's even harder to guess. In this case, I'm going to show you a formal way to determine if a given vector is a linear combination of other vectors or not. Okay. Essentially, we're trying to solve an equation of three vectors, a vector equation. Okay. These two question marks, I'm going to set the two question marks as two unknown numbers. I'm going to use variables to determine if there are two numbers. Okay, I will show you the official solution to this. Now the solution. Again, that's question 1A, part 1, question A. Part 1, question 1A, I guess, on the handout, on handout 5. Everything is available on D12. I'm saying this for the new guy. Okay. To determine if the given vector is a linear combination of the two other vectors, we solve a vector equation. I just told you that. Okay, we solve the vector equation. We're looking for two numbers in here. We replace the two numbers, the two scalars, with the two variables, two unknowns. So whatever you want to use. For two unknowns, I think we can just use x and y. Okay, we solve the vector equation. Now let's say, should I divide the whole thing into two? Okay, 3 negative 5 equals, now let's say x is the first question mark. That's a unknown number I'm looking for. Okay, x times 1 3 scalar multiplication. So here is scalar multiplication, and here this addition is vector addition. Okay, and then plus y times 2 negative 1. We're going to solve a vector equation like that. X and y are unknowns, are variables. I think we just call them unknowns. You're going to see we're going to end up with a linear system. The first question I'm going to show you more details. So, but in the future, it's easy to identify the system from the equation of three vectors. Okay. This equation is actually the same thing as that's IE. Okay, that is 3 negative 5. I hope I'm not copying anything wrong. Is equal to, we compute the right hand side. Okay, again here you have scalar multiplication. This addition is vector addition. So maybe I'm going to do that in two steps. The first question I'm going to run a little slower. Okay. X times 1 3. You treat x as a scalar. You treat x as a number. Okay. Scalar multiplication. I think you have x and then time. The second component is 3x. Scalar multiplication, all we need is to multiply all the components by the scalar, right? And then plus y times that vector. You have 2y, negative y as the two components. Again, we performed a scalar multiplication. Okay. And then we keep on going. 3 negative 5, the left hand side, so there's nothing you can do about that. And then the right hand side, you have now you perform vector addition. You add two vectors. To add two vectors, you add the corresponding components, right? So you'll have x plus 2y, and then the second component on the right hand side is 3x minus y. Now I have two vectors are equal. Now let's recall two vectors are equal if and only if they have the same components, right? And geometrically they are in the same direction and having the same length. We don't need that. Okay. Now you compare the corresponding components. you'll end up with a linear system. A linear system is something like this. You compare the first components. We write the system in standard way. Okay, we write the terms with unknowns on left hand side. Okay, so we have x plus 2y equals 3, and 3x minus y equals -5. I think you got the idea already, right? So basically, in general, to determine if a vector is a linear combination of other vectors, the problem is converted to solving a linear system. So that's my point. The problem is converted to solving a vector equation, and then it's furthermore converted to a problem of solving a linear system. Now all we need is to solve the system. We can use any method we learned before, right? In this course, I still prefer to use the matrix method. For Friday's quiz, I will restrict you to use the matrix method. Okay. Now we are practicing that. To solve the system, now let's do it together. Okay. So if you want, you don't have to watch me. If you want, you can try it yourself. Okay. We start from the augmented matrix. I told you this thing is going to be used over and over again later in the course. I do not write x. Augmented matrix is determined by the coefficients and the constant terms. The first row 1, 2, 3. 1 is coming from the coefficient of x, 2 is coming from the coefficient of y, 3 is the constant term, and then you have 3, -1, and then 5, -5. Again, you do not have to watch me if you know what's going on. If you want, I can review that. Okay. I'm mostly doing this for the new guys, or otherwise I would skip this actually. Okay. We perform elementary row operations. Make leading one of row 1. The circle number is already leading one of row 1. We do not do nothing about that. Okay. And then what do we do? We use leading one of row 1 to make all the numbers below that leading one zeros. We perform elementary row operation number 3. We add -3 multiple of row 1 to row 3. Okay. We multiply row 1 by -3 and add the multiple to row 2. Row 2. We add -3 multiple of row 1 to row 2. That's what I meant. I think I said something wrong earlier. Okay. Our target is to make this location 0. Okay. So row 2 is changed. This notation, it means a operation, a elementary row operation. The meaning is the new row 2 becomes the old row 2 at -3 multiple of row 1. Row 2 is changed. Okay. So you keep row 1, you'll have 1, 2, 3. I still circle that. This number is not the circle number is not going to be changed in the whole process. The process is called Gauss-Jordan elimination, right? This number is 0. That's what we wanted. We wanted to make this number 0. Okay. Okay, 2 times -3. You have -6. And then plus this 1. Do you have -7? Watch me, please. Okay. -7. And then -3 times 3, you'll have -9. -9, add this number, you have -14, right? I hope I got this right. So let me know if you see anything wrong, okay? Actually, I'm not super good at this either. And then, so we're done the first round. in the first round we make leading one of row 1, we make all the numbers so below that leading one zeros, and then in the second round we make leading one of row 2. Okay. We want to make this location 0. We want to make this location 1. We want to make this location 1 by performing some operations. There's only one operation you can perform now. Okay. We multiply row 2 by -1/7. That is the notation we want to use, right? The first row is now changed. 1, 2, 3. That's the leading one of row 1. That's the leading one of row 2. Again, the meaning of that operation is the new row 2 becomes old row 2 times -1/7. Row 2 is changed, of course. Okay. Finally, we want to use leading one of row 2 to make this location 0. Okay. The final form is called row reduced echelon form. Okay. We multiply row 2 by -2, and then we add a multiple to row 1. Then row 1 is changed. Okay. Again, the meaning of the notation is to add -2 multiple of row 2 to row 1. Our target is to make this location 0, right? So we're going to get the final form. Okay. The final form, row 2 is now changed, 0, 1, 2, right? And then row 1, so this number is now changed, leading one of row 1, leading one of row 2. At -2 multiple, so this number is going to be 0, right? We're adding -2 multiple of row 2 to row 1. -1. So you let me know if you see anything wrong, please. Okay. -2 times 2 is -4. -4 plus 3 is -1. I think we got this right. Okay. Again, the problem is converted to solving a vector equation, and then it's further converted to solving a linear system. If the system has at least one solution, then the answer to original question is yes. In this case, we see the system has a unique solution, right? And then the answer to original question is yes. It means that vector, now look at the mouse cursor, 3, -5, is indeed a linear combination of these two vectors. Okay. I will write the thing in some more details. Okay. So before that, you need to determine the system has a unique solution or not. Okay, has a solution or not. Okay, so the system has a unique solution. I will write the unique solution here. The unique solution is x equals -1, y equals 2, right? As long as the system has a solution, at least one solution, then the answer to original question is yes. I will show you how to answer the question. Okay. So thus, I forgot the vectors already. 3, -5, 1, 3, 2, -1. That vector is indeed a linear combination. I didn't leave enough space for myself. That vector is indeed a linear combination of this one and that one, right? As to say some vector is a linear combination of some other vectors, you say this one is a linear combination of some vectors S. I'm going to write that vector as a linear combination as, let's say 3, -5. Originally, to determine if this vector is a linear combination of these two vectors or not, all we need is to determine to find two numbers, two scalar, right? Now the two scalars we found are -1 and 2. Okay, -1. You do not have to write -1. So -1, 3. That's -1 times 1, 3, right? And then plus 2 times 2, -1. Of course, it's possible to check the answer. Okay, you compute the right hand side. As long as you have the left hand side, then the answer is right. Okay. Of course, we solve the numbers are coming from solving a system. The numbers, they have to be right. So, any questions? Any questions? If you don't have any questions, mute your microphone, please. To see what's going on in here, now we're going to do the second part. The second part is to let you see geometrically what's going on. Okay. Geometrically, I also want you to use a diagram to illustrate its geometric meaning. We'll do that. Okay. Everything is coming from the equation. Everything is coming from the equation. In order, it's easier to label the vectors. Okay. Label the vectors using something. I'm going to call this vector u. I'm going to call that vector v. I will call that vector w. Okay. So basically, I just want it's easier to label the vectors in diagram. I will show you what's going on geometrically. So this thing is going to be on Friday's quiz. We draw everything as position vectors. Okay. I hope I have enough room to illustrate this. Okay, U is the vector with two components, 3, -5. We draw everything as position vectors again. Okay. I will see the largest number, the smallest number we need. I think the largest number we need is -5. Okay. I will make the scale something like this. I will call that 1. Okay. That's 2. That's 3. That's 4. 5 maybe. Okay. That's -1. That's -2. Again, it may not be too accurate. Illustration only, as long as you see what's going on. It's fine. Okay. The first thing we do is, so basically we're going to represent U as a lead. I will show you what's going on. U is a linear combination of V and W as -V, right? And then plus W. And then plus 2W. Right? We'll get the vector U first. U has two components, 3, -5. 3 is here, so -5 is here. Initial point is the origin, okay? So the terminal point is here, 3, -5. Two components, 3, -5. So that's vector u. Probably it's better to label the vector on the. So temporarily, I just do that. Okay. So that's vector u. And then I also want you to sketch all the vectors u, v, and w. V is a vector with two components, 1, 3. Okay. Now let's say 1 on vertical axis, 1 is here. Now let's say 2 is here, 3 is here. Again, V is the vector with the two components, 1, 3. Two components, 1, 3.
Shouldn't it be negative, sir, because of negative v?
So later on, I'm going to do negative v. So basically, to illustrate, I want you to sketch u, v, and w, and also negative u and 2w. Now I'm sketching v. Okay. Very good point. I'm slower. I'm slower than you actually. Okay, so w is the vector with two components, 2, negative 1. 2, negative 1, right? Whereas 2, negative 1? 2, negative 1 should be, I hope it's not too messy, but 2, negative 1 is here, right? The first component is 2, the second component is negative 1, 2, negative 1 is here. That's not good. I could have made it bigger. So that's the vector w. I hope it's not too messy. Okay. On your piece of paper, I hope you can draw it way better than me. Now we want to illustrate why u is a linear combination of v and w. Okay. Equation is here. Very shortly, I will show you the general case. Okay. Equation is here. Now all we need is to draw negative v. Negative v, right? U is equal. Now you can look at that. Draw negative v. Negative v is using the geometric meaning. Negative v is in the opposite direction, the same length, right? As v, I mean. So negative v is, I believe, negative 1, negative 3, right? It's something like this. Illustration only, okay. That's negative v. And then we also need 2w. We also need 2w, right? Yeah, so w is here. W is here. Okay, now you look at the mouse cursor. So w is here. 2w is twice as long, in the same direction. 2w is here. Okay. And of course, if you compare the two components, it's better. 2w has two components, 4, negative 2. You see, it's kind of 4, negative 2, right? Now do you see u is a linear combination of v and w as negative v and 2w? I'm trying to say, I hope you see a parallelogram. You want to record the geometric meaning of addition? You see that, right? That's why u is a linear combination of negative v and that's why u is a linear combination of v and w as negative v and then plus 2w. Again, to illustrate this, you're going to see the question on Friday. A very similar question on Friday, I mean. Okay. I'm looking to ask you to sketch a few vectors. You sketch u, you sketch v, sketch w, and also sketch negative v and 2w, and try to identify the parallelogram. In this case, you see u is a linear combination of v and w as negative v and then plus 2w. You see everything, right? We computed everything by solving a linear system. Now we see everything geometrically. That's how we understand things, right? In any math. Actually, the same thing is true in general. So how about I will start a new slide. Okay, if I want you to, I do not give you numbers, I do not give you components. Still in R2, actually the same thing is true in R3. Still in R2, I will call that vector u. I will call that vector, so now let's say v. So whatever vector, okay, I will call that vector v. So now let's say whichever vector you want to be w, okay, as long as v and w are not on the same line. So can I call that vector w? Anybody want to tell me, is u a vector? Is u a linear combination of v and w? I'm going to write it down. Okay. For those three vectors u, v, and w. Now my question is the vector u a linear combination of v and w? Is u a linear combination of v and w? Okay, if you tell me yes, you have to draw me a diagram. So because u, v, and w they don't have components, right? I did not give you numbers. You have to use a diagram to illustrate. I will give you 1 minute to try to draw something. By drawing, I mean you get a scalar multiple of v, you get a scalar multiple of w, and then you make u the diagonal of a parallelogram. I will give you 1 minute, so please try to draw something. After that, we'll compare. Actually, the way is unique. The diagram you're going to draw, everybody is going to be the same. Again, you try something and then we compare the answers. Okay. Okay, now listen to me. I will show you what to do, okay? It's kind of you draw a dotted line so that the vector v is on that line, and then you draw a dotted line so that the vector w is on that line. Actually, you just make the lines as long as possible. Okay. And then what you do, now listen to me carefully, okay? And then what you do is to passing through the terminal point of u, it's here, okay? Passing through the terminal point of u. You want to make u the diagonal, right? Of some parallelogram. Passing through the terminal point of u, you draw a dotted line parallel to w, and then you draw another dotted line. It's parallel to v. It's kind of always the same. Okay. So do you see U is a linear combination? U is the sum of two vectors. U is the sum of the two vectors. I should have changed to different color. I will try to see if I can change the colors. Okay. It's a little clumsy, but I'm trying. So red is okay on black, I think. That's one vector. Okay. I think you see the other vector is here. Now do you see U is the sum of the two red vectors? You see U is the sum of two red vectors, right? I still don't like this color. Sorry, I'm a little colorblind. I cannot see red on black well. Now let's do yellow this time. Okay. Now you look at the mouse cursor. Okay. So what that vector? That vector is in the reverse direction as v, right? So because we do not have the components, you cannot determine the scalars. But that red vector is a number times v. The number is a negative number. Can I just say that vector a times v, right? That vector, the other red vector here is in the same direction as w, the same direction, right? So it's also a scalar multiple of w. The number is less than 1, of course. Okay. Can I call this vector bw? Again, we do not know the value of a. We do not know the value of b. So because we don't know how long u and v are, even, right? By that we mean we do not know the components of v and w. Okay. In this case, that's how you write u as a linear combination as v and w as a times v and then plus b times w. So that's how you see u as a linear combination of v and w. So that makes sense? It's always possible to draw a diagram like this geometrically. Okay. Now let's go back to this. It's always possible to draw a diagram like that, right? Algebraically, to get the scalar multiples, you solve a linear system. That's how we see two things. Again, the concept of linear combination is super important in this course. You need to get over this. Okay. We use a pretty long time to do a simple question. I think. But the question is pretty typical. Question is very typical actually. Okay. After this, we'll do question B. Okay, we'll move on to question B. In question B, I'm going to run question B a little bit faster. Okay. Okay, now look at the question B. Okay, on the screen you have question B. We are trying to determine a vector is a linear combination of two other vectors or not. Okay. We still use the formal way. I believe this time so people can guess, but we still use a formal way. Okay. Now the solution. To determine that, we solve a vector equation. The vector equation, so this time is very similar to before. You have 3, -5. I really should have give some notations for the vectors. 3, -5 is equal to x times maybe 1, 3, and then plus y times 2, 6. As long as you know what's going on, it's okay to go directly from the equation of 3 vectors to a linear system. Now let's try that. Okay. Now let's from the equation of 3 vectors to a linear system. Anybody want to tell me the first equation? The first equation, please. X plus 2y equals 3. Yeah, the answer is no. The answer is no. I think you are trying to tell me the answer. And then the second equation is 3x plus 6y equals -5, right? I hope I got this right. Okay. And then to solve the system, we use augmented matrix. The first row consists of coefficients of x, the coefficient of y, so which is 2. I think this number 3, 3, 6, and then -5 in here, right? You go from here, you perform elementary row reduction. I believe in one step you can see what's going on. You can see, and by the way, for a matrix, it's okay to use square brackets, it's okay to use round brackets, but try to be consistent. I still want to use square brackets this time. Okay. Now the first row is not changed, so leading one is here, right? We use leading one in the first row to make the number below 0. Okay, we want to make this location 0. I think you'll end up with something like 0, 0. Okay, -3 times 3, you'll have -9. -9 minus 5, still have -14. At this point, you do not have to continue. You'll see the answer. You see the solution to the system already. You see the system has no solutions, right? The system has no solutions. Look at the second row. Each row determines an equation. The second row determines the equation 0 equals -14, which is never true, right? The system has no solutions. What's the meaning of that? That vector is not a linear combination of 2 other vectors. So the answer to the original question is no. Okay. So that vector 3, -5 is not a linear combination of 2 other vectors of 1, 3, and 2, 6. If you want, we can we'll do the second part. Okay, I will show you why 3, -5 is not a linear combination of 1, 3, and 2, 6. I don't have to memorize the vectors. I will move this into here. We have seen the answer is no. Okay, so this time I'm going to call that vector as u. I will call that vector v. I will call that vector w. Okay. Actually, the problem is v and w. Anybody see why u is not a linear combination of v and w? V and W are on the same line. Yeah, that's why. Okay. I think you were trying to tell me that. Sorry, I didn't wait for your answer. V and W are on the same line. I will show you why. Okay, it's probably easier if we draw something. So now let's say 1 is here, 3 is here. So this time I'm going to draw illustration only. Okay, so probably that's vector v. That's vector v, right? So where's w? So w is 2, 6. So they're on the same line, right? 2, 6 is kind of that. That's a vector w. So that makes sense. Whatever linear combination of v and w you get. Okay, so can I say that way? What is the collection of all linear combinations of v and w? So by that I mean to get all linear combinations of v and w, you compute a v and then plus bw a number times v and then plus another number times w, right? That's you let a and b run through all the real numbers. I said you let a and b run through all the real numbers, and then you have a collection of all linear combinations of v and w. What is a description of all linear combinations of v and w? So does that make sense? Any linear combination of v and w are on that line, which means no linear combination of v and w is u. So where's u? 3, negative 5. 3, negative 5 is, sorry, it's not that. 3, negative 5 is kind of that. I hope it makes sense. All linear combinations of v and w are on that line, which means no linear combination of v and w is that u. So that makes sense. That's why u is not a linear combination of v and w. Actually, it's easy to do it by solving a linear system. It's pretty interesting to see it so geometrically what's going on, a linear combination. So
okay. So sir, if we had that question on like your assignment, do we have to show you it geometrically why it's not equal? Like, do you want us to do this?
On Friday, you are going to see a vector is a linear combination of v and w. So don't worry too much about this case. Okay. To say it properly, you just yeah. I guess I know your question. How to answer the question properly? Okay. I showed you the meaning. Use a diagram to illustrate geometric significance. Okay. I will try to write the answer properly. Okay. You say something like, so because v and w are on the same line, it's because of that all linear combinations of v and w are form, so maybe a better wording, form a straight line passing through the origin. Passing through the origin. Okay. This implies no linear combination of V and W can possibly be U. So clear enough, I hope. Okay, we did 2 questions. So maybe there's a better way to see that, but that's how I see it. Oh, again, algebraically, the system has no solutions. Vector equation has no solutions, right? So geometrically, that's how you answer the question. So geometrically, yeah, that's why. Okay, question C is simple. Okay, yeah, probably we did question C already. Is every two-dimensional vector a linear combination of two standard basis vectors? The answer is yes, right? It's easy to use. Okay, the answer is yes. I will show you illustration so geometrically. Okay. Now we are trying to the question number 3. I will give you a better solution to question 3. So the answer is yes. Okay. So because for every vector in R2, for each vector, so now let's say every vector in R2 has 2 components, right? For each vector in R2, so now let's say the 2 components are A and B. For each vector AB in R2, can I use V to denote the vector? So basically, V can be any vector in R2, and the vector has 2 components, AB. So that is the meaning of the notation. Each vector in R2. Now, let's recall the meaning of the standard basis vectors. In R2, there are 2 standard basis vectors. One vector is denoted using I, right? I has 2 components, so now let's say 1, 0. And the J has 2 components, so now let's say 0, 1. These are the meaning of the setup. Okay. So the answer is yes. We're trying to determine if V is a linear combination of and J for any vector V in R2. Okay. We say yes. So because for each vector V in R2, how can we write V as a linear combination of I and J? V is a linear combination of I and J as what? We are looking for 2 numbers, a number times I, and then plus another number times J. As long as V is given, A and B are numbers. Now we are looking for 2 numbers. I think all of you guys know that. Okay, A times I and then plus B times J. We have seen that on Friday, probably. Okay. Yeah, that's why the answer is yes. Algebraically, so that's how we see it, right? In terms of the definition. Now I also want you to see it so geometrically. Geometrically, where are the standard basis vectors? That's x-axis, that's y-axis. That's 1 on the horizontal axis. So now let's say, so that's 1 on the vertical axis. Origins here, right? I has 2 components, 1, 0. So the terminal point 1, 0 is here. So that is the standard basis vector I. So that makes sense? That is the vector J. Right. And then for any vector AB, for any vector AB, I think it's easier if you imagine AB using some particular numbers. So now let's say 2, 3. 2, 3. I'm illustrating using AB, but you imagine A is 2 and B is 3. Okay. So now let's say, now you look at the mouse cursor. 2 is here, 3 is here. Okay. Now let's say I'm drawing vector V using some random numbers, like 2, 3. I think 2, 3 is something like this, right? So do you see how do you see it? I think that's AI, right? So that's AI. You imagine A value is 2 and B value is 3. Sorry. So that's 2i. I think that's AI. And likewise, you have a BJ in here, right? So do you see V as a linear combination as I and J? U is a linear combination of I and J as AI and then plus BJ. You see a rectangle in here, right? That's the geometric meaning of any vector in R2 is a linear combination of I and J. I hope it makes sense. Again, if it's too abstract for you, if I using A and B, you replace A with 2 and you replace B with 3. Any number is actually the same thing. Okay. So good enough. The beginning of the class, we mentioned 2a. Okay. I think we did all the questions in question 2 already. Okay. In question B, is every vector in R3 a linear combination of the 3 standard basis vectors? And why? Actually, the same thing, right? Again, in R3, the standard basis vectors are ij and k. I told you how to form ij and k already. Only one of the 3 components is 1, so the other 2 components are zeros. That's how you get ij and k. I think the answer to B is yes. I did not ask you to illustrate geometrically, but you imagine it's possible to illustrate in space geometrically, right? You did question 3 on your last quiz, on Friday's quiz. I will show you how again. So these questions, the questions like question 3 are designed for the definition of linear combination. So very quickly, okay, very quickly. Is 0 vector in R3 a linear combination of UV and W? The answer is yes. If I'm looking for y, you give me an equation something like this. The 0 vector is a linear combination of UV and W as 0 vector is a linear combination of UV and W as I'm looking for 3 numbers. 0, the number 0 times U and then plus the number 0 times V and then plus the number 0 so times W. So don't be confused about the operations we are doing. Okay, that's the vector 0 vector. Now look at the mouse cursor. This one has 3 components, right? A 0 vector, the 0 vector with 3 components, 0. Okay, that's the number 0. That's number 0. That's real number 0. Scalar multiplication. You look at the mouse cursor. Scalar multiplication. Vector addition. So don't be confused. Okay, not every addition is a addition of numbers. Now we're talking about the context is for vectors. Okay, I hope it makes sense. Now question 2, is U a linear combination of U, V, and W? U is one of the three vectors. I'm trying to show you one of the, if a vector is one of the vectors in a collection, then any one vector in the collection is a linear combination of the collection of the vectors. Okay. It's easy too, right? U can be written as a linear combination of V and W, as U is equal to so just 1 times U and then plus 0 times V, a number 0. And then plus the number 0 so times W. Okay. Again, so don't be confused about the operations. We have vector addition, scalar multiplication, and so on, right? A linear combination is a combination of numbers, scalar multiplication, and vector addition. Linear combination. I hope the term so makes sense to you. Linear combination, right? Any questions so far? I think we're done all the questions about so linear combination. But the concept is going to be used over and over again later in the course. Okay, when we talk about vector spaces, linear transformation, linear maps, we're going to use them over and over again. Any questions? If you don't, we move on to the next topic in chapter 1. Any vector has a length and direction, and then how we describe the length and the direction. The length is just the geometric length, how long the vector is. Okay. I believe you can guess the formula, but the formula is coming from the Pythagorean theorem. Okay. But I'm going. Okay. I will tell you why the formula is true. So probably it's easy. Now the next topic, so we're talking about is the length of the vectors. If you look at the handout, we are on the section 1.2. I don't know if it's consistent with the section name on the new textbook or not, but I'm referring a textbook I used to use, so don't worry. We're talking about the length now. Okay. A simple case. So how about I'm going to make some nicer numbers. For a vector with two components of 3 and 4. Now let's say I'm drawing a vector, so now let's say U has two components. So now let's say 3, 4. Okay. I will treat U as a position vector. So now let's say 3 is here, so 4 is here. Okay. Anybody want to tell me the length of the vector? How long the position vector is? It's simple. I'm looking for answer. Anybody want to tell me the length of the vector U? How long that vector is? In a right triangle, so that side has the length of 3, that side has the length of 4. Okay, it's 5. It's 5. The length is 5. Okay, we use a notation like this to denote the length. The length of a vector U is denoted using a notation like this. this notation is for the length of u. It's not the absolute value. You write 2 bars on 2 sides. Okay, the length of the vector u in this particular case is computed using square root of the sum of the squares of 2 components. Square root of the sum of the squares of the 2 components. You take the squares of the 2 components, 3 squared and the 4 squared, and then the sum of the squares of the 2 components, right? And then you take square root, right? So that's how you get the length of 5. You told me the answer is 5. You see the answer is 5, right? Okay, I hope we're going to generalize that. Now we're going to generalize the conclusion. I think we treat the thing as a definition. Okay. For any vector v in Rn, now we're going to generalize to any dimension. Okay, to Rn. Now let's recall Rn is the set or the collection of all the n-dimensional vectors. Each n-dimensional vector has n components, right? You can imagine the length or the norm using that notation. Okay, it's defined that way. I think you can see why we define that way, right? That is the formula for getting the length of the vector. Okay. I really do not think you need too many questions, so maybe I'm going to do only one question. Okay, as long as you know all the components, you use the formula, you can get the length. I'm looking for the handout. Okay. I will do only question B. Okay. In question B, you are given a vector AB. You know the initial point, you know the terminal point. We are looking for the length of the vector. I did not copy the question, but the question is asking you to compute the length of the vector AB. A is initial point, B is the terminal point. Okay. So before we do anything, we have to compute the components of AB, right? Now let's recall how, if you know the initial point and terminal point, how can we get the components of the vector? AB is a vector having 3 components, right? Now let's compute the 3 components. The first component is computed using the difference between 2 x coordinates. The x coordinate of B minus the x coordinate of A, right? I will do that in some more detail. Okay. The first component is coming from 2 minus 1. The second component is coming from -1 minus 2, right? The third component is coming from 0 minus 3. Again, it's the difference between the components of the terminal point and the initial point. Correspondingly, you have 3 components. I believe the first component is 1. Second component is 3, negative 3 I mean. Third component is also negative 3. Right? Again, the formula for computing the length showing you as long as you know all the components, and then you can get the length of the vector. That's why the first thing we do is to get the components. So that makes sense? Now we are ready to compute the length, okay, or the norm. There's alternative name, norm. So we just call it the length. Okay. So the length of the vector AB, the length of the vector AB. Now remember the term, the notation. You write 2 bars on 2 sides of the vector. It's computed using square root of the sum of the squares of all the components. So you have 1 squared and then plus negative 3 squared, and then plus negative 3 squared. Right. I made a mistake on purpose. So here the square, it means the whole thing squared. Let's be careful. Okay. If you do not include brackets, so I'm trying to say negative 3 the whole thing squared is equal to positive 9. Okay. This means you multiply negative 3 itself twice. If you do not include squared, you have negative 3 squared is equal to negative 9. So don't be confused. Okay. In this context, we mean the whole thing squared. Okay. Final answer, please. Final answer: square root of 9 plus 9. You have 18. So do you have 19? Square root of 19, right? In this course, you do not have to convert the square root to decimal. You can just leave the thing as answer. Okay. You can leave it as the final answer. Do not have to convert the thing to decimal. This is better than converting. Well, however you convert, that's a irrational number. It's not accurate. So this number is accurate. Okay. But if you have a number like square root of 8, you have to simplify. Okay. You have to simplify to something like this. 4 times 2, right? 8 can be written as 4 times 2. You have to simplify. I'm trying to say square root of 19 is can be treated as the final answer, but square root of 8 is not the final answer. You have to simplify. I think the same as high school. That's kind of the same thing. These are not part of the solution. I'm going to remove this. Okay. Easy, right? The length is easy. And also a vector has a length, has a direction. And then how can we describe the direction of a vector? We're going to use a unit vector, the unit vector, in the same direction as each vector. Okay. I will make a little comments on y. I will call this vector u. I'm going to call this vector v. Okay. These two vectors are in the same direction, so geometrically. Algebraically, how can we define the direction? What's common about the two vectors? I'm trying to say we're going to use something common about all the vectors in the same direction to describe the direction of the vector. What's common about the two vectors? The unit vector is common. Is the common thing. Okay. The unit vector, by unit vector we mean a direction with a vector with the length of 1. So that makes sense. We call a vector with the length of 1 a unit vector. Very shortly I will show you the definition. Okay. So now let's say 1 is that long. 1 is that long. That's the unit vector in the same direction as u. That is the unit vector in the same direction as v. These two vectors are always the same as long as two vectors have the same direction. So that makes sense? Okay. You do not have to fully understand that. As long as you know how to get the vector, the unit vector in the same direction as a given vector, yeah, that's fine. Okay. I'm going to show you the formula. The formula is here. The formula is here. Okay. Now you look at the screen, so that's from the notes. You do not have to copy this for the new guy. Okay. A unit vector is a vector with the length of 1. That is the definition. And it's computed that way. Okay. If the notation is u is the unit vector in the same direction as v. Okay. And then the vector u is calculated using that formula. Now you look at the formula. 1 is a number. On denominator you have the length of v. If v is not 0, then the length of v is a non-zero number. I'm trying to say the fraction is defined. Okay. Now the whole thing 1 over the length of v is a number, a scalar. On the right hand side you have a scalar multiplication. So that makes sense? A number times a vector. I will copy the definition here. Okay. Okay, so because of time, I just go over the solution on the PDF. Easy, okay. I will show you the meaning. Now, in this question, we are trying to get the unit vector, okay, in the same direction as v. In order it's easier for me to make some comments, I'm going to copy the solution to the PDF, to the PowerPoint. I mean. Okay, now you look at the solution. Now in the question we are trying to find the unit vector. Okay. The unit vector u in the same direction as v. Okay. You know the formula. Okay. The formula is here. Again, now look at the cursor. The whole thing in this circle is a number. Okay. I just mentioned. Okay. To compute the number, the 1 is on the numerator. The denominator is nothing but the length of v, right? The length of v. You see, it's a number. The number is 1 over square root of 14, and then you use the number to multiply the vector, a scalar multiplication. The final answer is something like this. You can check this vector u has the length of 1. This vector u has the length of 1. I will convince you. Okay. Now you are done the complete solution. I'm now making some comments. To compute the length of u, I'm convincing you the length of u. So this part is only comments. Okay. It's not part of the solution. The length of u is computed using the sum of the squares of the 3 components, and then you take square root, right? Square root of 1 over 14, now the whole thing squared, and then plus 3 over 14, the whole thing squared, and then plus 2 over 14, the whole thing squared. Square root of 14, I mean. I'm sure under the radical you have 1. So, which means the length is 1. Okay. That's why the resulting factor u is actually a unit vector. A vector with the length of u is 1. So you have seen that. Okay. I'm pretty sure some of you guys are are going to take calculus 3, calculus 4, if you are in some so engineering program or something, okay, you're going to take calculus 3, okay. So they think it's going to be useful in calculus 3. I will show you the geometric meaning of the unit vector, so in the same direction, okay. In 3 space, in the space, I told you the setup before, right? So now let's say that's x-axis, that's y-axis, that is z-axis. Again, for the people who are going to take calculus 3, you're going to need this, the following, okay. So now let's say the vector u is a unit vector. Now let's say the unit vector is here. That is the vector u, okay. I'm telling you the meaning of the vectors, the meaning of the components, okay. In this particular case, the first component, the first component, 1 over square root of 14, is actually the cosine value of the angle of u and x. So can I just use I? So by that we mean, now look at the mouse cursor, okay. There's a angle so between u and the positive direction of x-axis. Cosine value of the angle is the first component. This is not going to be tested in this course, but you're going to use this in calculus 3. And likewise, cos value of v and j, sorry, u and j. Is equal to the second number, 3 over square root of 14. And likewise, cos value of u and k. K is the unit vector on z-axis, right? Is equal to the third component. So now let's say 2 over square root of 14.